Hey everyone, welcome to this explainer. Today, we're tearing into a super fascinating chapter from a standard computer architecture text, and we've tailored this specifically for those of you who want a direct, no-nonsense understanding of how our devices actually work under the hood. We're setting out to demystify a really crucial piece of the puzzle, how the hyper-fast brain of our computers, the processor, manages to talk to the incredibly slow outside world of keyboards, monitors, and drives. Honestly, it's an amazing story of architectural evolution.
Okay, let's dive into this. It's kind of the ultimate engineering puzzle, right? If the processor is the undisputed brains of the operation, why do we need all this complicated, sprawling architecture in between? Like, why can't you just wire a keyboard directly to the system bus of the processor and call it a day? Well, it basically boils down to three massive mismatches. Think of the processor as this hyper-caffeinated, incredibly focused genius. The peripherals, on the other hand, they're kind of like a diverse, much slower-moving public. First off, there's just a gigantic variety of devices out there, and it's totally impractical to build all their specific operating logic straight into the processor itself. Second, the speed differences are absolutely dramatic. Processors are operating at these blinding, microscopic speeds, while a keyboard is literally just sitting there waiting on slow human fingers. And finally, these external devices often use completely different data formats and word lengths than the processor does. So, to make sense of this absolute zoo of hardware, the computer has to categorize the massive variety of devices it interacts with into three distinct groups. First, we have human-readable devices, things like video displays and printers. Then we have machine-readable devices, which include your magnetic disk drives, tape systems, and sensors. And finally, the communication devices. These are things like modems that allow the computer to exchange data with remote devices, like another computer halfway across the globe.
Just to make sure we're all on the same page here, let's quickly establish a solid foundation with a clear definition. An external device connected to an I/O module is officially what we call a peripheral device. But here's the key. A peripheral doesn't just blindly send raw data. It's an active conversation. It exchanges control signals, status updates, and data bits back and forth with the computer.
And this brilliantly illustrates exactly how this works in practice. Up at the top, you've got the system bus, which is basically the high-speed exclusive highway for the processor and memory. Down at the bottom are the slower links out to the peripheral devices. And sitting perfectly right there in the middle is the I/O module. It acts as this vital translator and traffic cop, bridging the enormous gap between the blazing fast internal system and all those diverse external devices.
So, what's this middleman actually doing all day? Well, its core functions are laid out right here. It handles control and timing, basically ensuring traffic flows smoothly without any crashes. It communicates heavily with both the processor and the specific device. It's constantly on the lookout for errors, whether that's a paper jam or a corrupted transmission. But I want you to pay special attention to data buffering. Because a peripheral is so agonizingly slow, the I/O module will receive a rapid-fire burst of data from the processor, buffer it, and then sort of spoon-feed it out to the peripheral at a speed the device can actually swallow.
All right, moving into our next section, the evolution of delegation, from micromanaging to outsourcing.
If you look at the big picture here, we're basically tracking the evolution of a highly stressed boss learning the fine art of delegation. We're going to look at three evolutionary stages of how a processor interacts with the I/O module. At the top, you have the older techniques where data transfers had to physically pass right through the processor itself. That's programmed I/O and interrupt-driven I/O. But down at the bottom, we see the absolute breakthrough. Direct memory access, or DMA, where data goes directly to memory. Let's step through each of these, because seeing how this evolved is crucial to understanding why modern computers are so fast.
Let's start with Method 1, Programmed I/O, or, as it's better known, the highly inefficient past.
Okay, picture the absolute worst micromanager boss you've ever had. They give you a task, but instead of going back to their office to do their own work, they literally stand over your shoulder asking, "Are you done yet? How about now? Are you done yet?" every single second. In programmed I/O, that is exactly what the processor does. It executes a program giving it direct control of the I/O operation. It issues a command, and then it just constantly interrogates the I/O module to check its status. It gets trapped in this endless waiting loop until the operation completes. Because the processor is infinitely faster than the I/O module, this is a colossal waste of precious computing time. I mean, it severely degrades the performance of the entire system.
Moving on to Method 2. Interrupt-driven I/O, the old tap on the shoulder. Now, what's really interesting about this slide is how polite the system gets. Clearly, sitting around waiting wasn't sustainable, so the architecture had to evolve. Here, the boss finally learns to go do other valuable work until the employee physically taps him on the shoulder to say the task is ready. The processor issues a read command and just walks away to work on other programs. When the I/O module is finally ready, it shoots an interrupt signal over to the CPU. The processor calmly finishes its current instruction, acknowledges the interrupt, saves exactly where it was, its context, and then transfers control over to an interrupt handler to go grab the data. Much better, right?
So comparing the two side by side, interrupt I/O is a massive upgrade over programmed I/O because it completely eliminates that endless, mind-numbing waiting loop. But there is still a glaring bottleneck here. With both of these early methods, every single solitary word of data that moves from the I/O module to memory must still physically pass through the processor. The boss doesn't have to wait around anymore, sure, but they still have to carry every single heavy box themselves.
Which brings us to Method 3, Direct Memory Access, or DMA. This is a total masterclass in delegation.
See, for moving real heavy volumes of data, relying on the processor to touch every single piece is still just way too slow. The industry needed an ultimate solution, and direct memory access fundamentally flips the architecture on its head. DMA is a technique where an entirely separate, specialized module on the system bus is capable of mimicking the processor. In this mode, the I/O module and main memory exchange data directly with each other, completely bypassing the processor.
Looking at the architecture here, the DMA module basically steps up as a stunt double for the processor. Because it's outfitted with its own address register, data count register, and control logic, it can literally seize control of the system bus. It becomes completely dedicated to the grunt work of moving data, totally freeing up the main processor to do what it was actually built to do: compute.
Let's move to and see how this builds out practically into a highly efficient system. When the processor realizes it needs to read or write a huge block of data, it just delegates the whole thing. It fires off 4 quick pieces of information to the DMA module. Hey, is this a read or write? What's the address of the I/O device? Where do I want this to start in memory? And exactly how many words are we transferring? Once the processor hands over that little clipboard of instructions, it's completely done. It washes its hands of the situation and goes back to its real job.
Okay, there's always a catch, right? In this case, it's a little quirk known as cycle stealing. Because the DMA module and the main processor are forced to share the exact same system bus, they obviously can't both use it at the exact same millisecond. So to transfer a word of data, the DMA module occasionally forces the processor to just suspend operation temporarily. It literally steals a bus cycle. Now, the processor doesn't have to go through the whole song and dance of saving its context like it does for an interrupt. It literally just freezes for a microscopic fraction of a second.
As the text clearly puts it, quote, "The overall effect is to cause the processor to execute more slowly. Nevertheless, DMA is far more efficient," end quote. Even though the processor takes these tiny little stutters for cycle stealing, keeping it out of the tedious, heavy-lifting business of moving bulk data word by word is a massive system-wide win. The processor is only ever bothered at the very beginning to set it up and the very end when the job is done.
So, the crucial point is this. We generally walk around thinking computers get faster simply because processors get more powerful. We stare at gigahertz speeds and core counts on the box, right? But raw power is really only half the story here. If a super genius brain is constantly bogged down doing menial, painfully slow data entry tasks, the whole system is going to grind to a halt anyway.
It turns out, modern computing speed relies just as much on smart architectural delegation as it does on raw processing horsepower. Through this brilliant evolution, from programmed micromanaging to polite tapping on the shoulder with interrupts to the total outsourcing of direct memory access, engineers built a system where the processor does what it does best. So I'll leave you with this. The next time you're streaming a massive 4K movie or loading up some giant open-world game, just ask yourself, isn't it kind of amazing how much invisible, heavy-lifting delegation is happening in the background, entirely bypassing your processor just to make that experience possible? See you in the next explainer.